Hi, my name is Charles. I'm the co-founder of Titan Robotics. We're a manufacturer of thrust measurement tools, and today I'm going to talk about the most common protocols that are used between the ESC and the microcontroller, including the ones that are supported by our tool. So the legacy signal that's always been used is a PWM at 50 Hz. Originally, that signal was intended to be transmitted over an analog wireless transmission, and you had typically control of between 6 and 8 servos. So in a single signal here, you had, for example, servo 1, 2, 3, 4, 5, 6, and 7. And the standard in that protocol was that every update happened every 20 milliseconds, and the length of each pulse determined the control signal. And the standard at the time was that 1000 microsecond or 1 millisecond corresponds to approximately 0%, and 2000 microsecond corresponds to approximately 100%. On your small radio control aircraft, you had a box that would take that wireless signal and separate it into 6, 7, or 8 signals, and then you had a single signal like this that was transmitted to your servo. When we started developing quadcopters, we realized that there's a whole lot of time available between the two update signals at 50 Hz, 20 milliseconds to be exact. And that's how we got PWM at 300 Hz and eventually 490 Hz. You might wonder why not go faster than 490 Hz. And that's because at 490 Hz, the update happens every 2.04 milliseconds. And if you remember, our 100% signal value is represented by 2 milliseconds. So if we were to go faster, we would not be able to distinguish between a fault, which would be, for example, a 5-volt signal that's sent to your ESC, and an actual 100% command. That could be actually quite dangerous in some cases. When we look at PWM 490 Hz, we see that there are some further optimizations that can be made. The main one has to do with how the CPU sends the update to the ESC. If we look at the typical control loop, you're going to have your sensors that sends the data to the CPU. The CPU will perform mathematical operations, and then it will determine what signal to send to each of your ESCs. In PWM 490 Hz, if your update rate happens here, if your control loop finishes here, you're going to have to wait almost 2 cycles until your ESC can receive the proper signal here. In the worst case, that is 4 milliseconds. And not only is it 4 milliseconds, but it's also not consistent. In some cases, you could have a latency of 1.5 milliseconds, and in another case, you can have a latency of 4 milliseconds. That's not ideal. It could have performance implications, and it's also not as fast as it could be. If you synchronize your update with your CPU update, and you also reduce your 100% value from 2000 microsecond to 125 microsecond, you obtain one shot. This is a faster protocol, and it gives you some performance update. More recently, we have seen UAVCAN used on larger drones. UAVCAN is a digital protocol, meaning that you no longer have signal length, but now you have ones and zeros that are exchanged. It's in the megahertz range, so you have much faster data transmission. It's also differential. That means that you have 2 signal wires, and each of those are sending an inverted value. This is better to resist and reject noise, especially when you have high-power ESCs and noise that can be coming from lightning or thunderstorm. Overall, UAVCAN is a more robust protocol. This is what is typically used in the automotive industry, for example. And finally, it's bidirectional, meaning that you can get data back from your ESC. This data could be ESC temperature, for example, and that can be used to monitor the health of the ESC. Overall, that increases safety of the whole system. That concludes our summary of ESC protocols that are commonly used. We've made a lot of effort to support as many ESC protocols as possible with our tools. If you want more information, don't hesitate to contact us or leave a comment below. Thanks for watching.